Okay, I want to talk to you about, and this is it's sheet 4.1, and for spring of 2009, it's sheet 4.1, but let's go ahead and just call it. Okay, I'm going to put 4.1.10, but in coming years, they're not going to know it's that, so I'm going to say it's investigation 7. Expansion 2, intro to free body diagrams. That way, I'll list it as out of the table of contents both ways. Okay, so we're looking at number 10. We already showed you number 7. This one is the little boat. So let's go with our X and Y axis. And anytime you have an angle, you need an X and Y axis. And so the forces on the boat, we're going to have, it's towed by a big ship at 10 knots. Now remember, a knot is a nautical mile per hour. It's like speed. And so they used to have a rope that threw the log over, and then they'd have knots tied in it, and they would, how many knots went through their hands as the boat moved on would be their speed. And so that's where they get the word knot. Here we have the boat, and the first thing I'm going to do, first thing I probably always do is put the, I'll put these a little bigger, is put the force of the weight. Now, you always need to do these free body diagrams in pencil because you end up having to change your lengths of your arrows. So if it's a quick sketch in a problem and it's a test and it's a blue pen day, then you really have no choice. But if it's a problem where you have to use, you're going to have to adjust it, I'll probably let you use a pencil on that part. I don't know, something like that. But anyway, it has, so this thing has a weight, and the next thing it says it's being towed at an angle of 35 degrees. So we have this tensile force of pull. I could put tension on there. I'm going to call it force of pull for now, and I'll make it that long. And that's the, I may end up making these the wrong size to begin with. That's okay though, because the first thing you want to do is establish what forces you have and what angles you have, and then you can adjust knowing how vectors add up. Remember, the idea is the resultant vector may either be 0 if it's a static case or an equilibrium case, or it'll be in the direction of motion if there's movement involved, if there's acceleration involved, or positive or negative. Ooh, I take it back. So the resultant force is either going to be in the direction of motion, or it's going to be opposite the direction of motion. We didn't bring that up in class, but it's opposite the direction of motion in the case of deceleration, the resultant force. We'll get to that. So we have the weight of the ship down, the little boat, and then this big ship over here pulling on it. And then there is a force up. Now the force up is not a normal force, because remember, normal force you have to have this, 2 solid surfaces. If you don't have 2 solid surfaces, there is no, you don't call it a normal force. In this case, it's being held up by water. So we talked about Archimedes' principle, about the amount of water displaced. It's going to then cause buoyancy, and because the pressure is higher below, so it's going to push that boat up. And so there is a sense of buoyancy. There is a force of buoyancy up. Now I don't know the length, and remember, for buoyancy is a capital B. We put a subscript W to indicate its buoyancy of water. Air or any kind of gas has a buoyancy. Water has a lot more, obviously, because there's a lot more pressure in water to push up. And then this thing is moving in this direction. I probably should have put that there. The way we're going to do motion is I'll put an arrow showing the direction of motion. Let's get rid of this. And I'll put a DOM here. In this case, it's like that. But that'll be a place, this is a new this year, but that'll be a place where we can put, because you can't show a velocity vector. A free body diagram, technically, to be a purist, only has forces. Doesn't have anything else. There's no other vectors on there but forces. So I don't want to complicate it, even with different color. I don't want to complicate it with the velocity vector. So I'm going to stick the velocity inside here. It's 10 knots. So I think that's going to be a good place for us to put other information, maybe inside the big arrow, rather than just make it yellow. Put something inside the big arrow. Okay, so 10 knots. And That's a constant velocity, by the way, constant velocity, which is going to be important. So let's keep going back with our forces. If that's my direction of motion, I saw some students when you came to the board, you did this, and you said that was your water drag. Well, the problem is, if this were a dolphin coming out of the water or something, or a shark, whatever, coming out of the water and it was coming in that direction of motion, if it was moving up, then I would agree. But this boat is moving this way, so that's wrong. That needs to, it's a frictional force, and so it needs to oppose motion. So your resistance is going to be back along this. I don't know how long yet, but I know it's in that direction. So there's my RW. Okay, so you've established all your forces. Those are the only four. Now, some students have put a little RA back. I'm not going to argue with them on that. That's okay. I mean, it's only going at 10 knots, which is not that far from 10 miles an hour. So not a lot of velocity there as a problem. But you might have a real big profile area. It might be a tugboat or some real big profile area on the boat you're towing. It just says a little boat. So I'm assuming like a raft or canoe or something. So probably not much RA back. Okay, so there's my forces. Well, now I want to establish that I have the lengths. I know I have the directions right and I labeled them right, but are the lengths correct? And the way you do that is they have to add up to the resultant force. Now, here's the question. What's the resultant force? Well, the resultant force in the in the y-axis, since this boat is not levitating out of the water, it's not sinking in the water, I know that the summation of my forces in the y-axis must be 0. So I could go along, I suppose, right now and put down the equations. Yeah, let's go ahead and do that. Let me get some room here. Go ahead and erase this up here for now. Erase the title. Okay. And let's put the forces, let's put the equations. And so summation of forces in the x and the summation of forces in the y. Okay, so we're looking at Newton's second law, the way we write it today. And so we have FP. This is going to help me, I think. Sometimes you might want to do your equations first, then go back and look at the lengths of your force vectors and see if you need to adjust them. That's wrong. It's not a force of propulsion. We're calling it, okay, you caught me. I was calling that force of tension, but we've established in this class that that's going to be force of thrust. And there's no thrusting going on here. Thrusting is like a rocket. So my bad there. Let me get rid of that. Let me change that to an F of P. We'll talk about tension later. So F of P there. So force of propulsion. It's, you know, it's not. There's not a propulsion here. Oh well, we'll call it force of pull. All right, that's fine. So F sub P times cosine of 35. No, someone asked. Remember, the vector is the hypotenuse of a right triangle. Any vector at an angle is the hypotenuse of a right triangle. So let's get our right triangle that I'm talking about. If I drop this down, and the right triangles we're going to make are going to emanate from the x-axis. As long as our angle comes from the x-axis, the right triangle comes from the x-axis. And let's go ahead and fill this in. Nice little orange, a little green to be good. Let's fill in our triangle. And remember, every vector at an angle is going to give you a right triangle. Okay. So, all right. So this is my FPY, and this is my FPX. And someone said in an hour, well, can we call that I? Can we call that J? Yeah, I mean, it's a unit vector. The I and the J gives it its, say the I says it's in the X direction, the J says it's in the Y direction. But remember that from trigonometry, this is the adjacent side to that angle. And this is the hypotenuse. And so we have always the adjacent side is always the cosine, right? Because the adjacent over hypotenuse is cosine. So that's why I put cosine 35 on the adjacent side, and I'll put sine whatever the angle is for the y or for the opposite side. Okay. So here we go. Let me make sure that thing's still recording. I don't see a light. There's not a light on it. And yeah, we are. Okay, good. All right, so just kind of used to this new camera. So FP cosine, that's a positive in the direction of motion, minus I get all my RW, my water drag, and there's nothing else. This doesn't play any role in the x direction. It's straight up, straight down. We don't worry about it. And that's got to equal what? Well, some of you put MAX. Now, technically, you're not wrong, but you could be more correct, okay? Not saying you're wrong, but at a 10-point problem, you lose a point there because you could be more thorough and be more explanatory. It's what you want to be with the free body. It's your thesis statement, so you want it to explain what your problem's all about. Well, there's no acceleration. See, 10 knots is a constant velocity, therefore there's no change in velocity, therefore there's no acceleration. So A is actually 0, and so I can make that better by saying equals 0. Okay, so there's my force in the x. Now my force in the y direction, let's look at all those forces. I'm going to get part of this. So I'll get FP, now it's in the y, sine of 35, plus BW, the buoyancy, I get all of that one, minus mg, it's going to get all that one down, no RW, does not play a role, equals, and once again, like I said earlier, not levitating, not sinking, therefore no motion, it's actually static in the y direction, so 0. So these are 0 for two different reasons. This one's a 0 here because no acceleration in equilibrium. The forces are in equilibrium in the x direction. And this is 0 because the forces are, yes, they're in equilibrium in the y direction, but in addition to that, they're static. So there's a difference between static or the difference between equilibrium and static equilibrium. Okay? Newton's first law holds in both cases. There's no unbalanced force up or down, so therefore it's static. But there's no unbalanced force left or right, therefore there's no acceleration. Okay? Now I also saw some students do this when they came to the board. They put a congruent sign here and here, and that looks right, but it's not, because in addition to the BW up, we also have FPY up, or FP sine 35. So we have two forces up and one force down. So this is not correct. You don't want to put those congruent symbols there. All right, so there's everything we need. There's your symbol equations, and this is problem number 10 from that sheet. Very good. Okay, well, I'm coming back on this one because I realized as I was working on the problem, this, by the way, once again, this is problem number, just to put it back up, this is problem 10. And so I realized that I didn't go back and check. After I did this, I never went back and checked the lengths of my arrows. They have to work out because when I add up my arrows head to tail, my vectors head to tail method, I'm going to have to, according to this, I'm going to have to end up with no resultant in the x and no resultant in the y, therefore no resultant period. So going through, and there'll be a worksheet and a few worksheets from now, we'll do this with rulers and protractors, but right now, going through this vectorially, this is component-wise, but head-to-tail method, it would be this. I'll make sure you can see all that. Sorry, I'm still learning the limits of this camera. Oh yeah. We're in great shape. Okay, so what I'm going to do here, watch this, don't freak out, but I'm going to say the vector of buoyancy, water buoyancy, plus, and I can just add them. See, I'm just going to add them up. I say, wait, why say minus? You should say minus that. And whoa, Mr. Askey, why are you putting x and y's together? Because now I'm taking head-to-tail method, which just means you take all those vectors like you did back in, way back when, back in October or so, when you took those arrows and you put them all together. See, everything we do comes back later on in physics. We don't waste any days in here, hopefully. Everything we do may not seem like it has a reason at the time, but it does. You cannot blow it off. And there's FP, and then I got one more, and that's mg. So plus mg. So all of these, I emphasize that it's, and this is going to all equal 0, no resultants. I wouldn't, normally I'd put an equals r, right? but I know there is no resultant. So there's my 4 forces. So that means that when I take my 4 arrows and I put them together, I'm going to get a quadrilateral, not a pentagon. If there was a resultant, I would get a pentagon because I'd have that extra, you know, R. Hopefully that makes sense. Replay it again if it doesn't, but think about it. But when I add up these 4 arrows, I'm going to have no resultant, so I'm going to get a quadrilateral. So that's the game I got to play now. I got to think, how am I going to adjust my length? I know my direction's right, I know that labeling's right, but how am I going to adjust my length? Obviously I got a problem, I can tell right off the bat, because in the X direction, this component, this part of the FP, has to be the same length as RW, because those are the only 2 vectors I have in the X direction. They have to add up to 0. So I'm either going to make that smaller, which would be a hassle, or just make that bigger. So I'm going to make that bigger. So I'll take this, so I'm looking at 15, 16, okay. So come right here, I'm going to make it right to there. So that's going to get that small, get rid of that little arrow, and continue that on over to here. Okay, so there's my new RW. And now that's the right shape. There's a lot of water drag, but it is, because it's probably a pretty big profile area of dragging through water. You know, it's hard to do that. And then this plus this guy, these 2, must add up to that. So obviously the easiest way to do that is just to add down here. So let's go ahead and get rid of that guy. And let's make it so that when I add these 2 up, let's do it this way. Okay, so that's about 20 centimeters, and that's about 20, so about 40 centimeters for this guy. 40. So it looks like my MG goes all the way down. MG goes all the way down to there. Woo! So there's my MG. Now that is the correct lengths. Because when I take, you can do this, and you put this, watch this. And now it's got to be head to tail. Okay, if I slide, that's tail to tail. These are all, everything's tail to tail to tail to tail. No good. You can't, that's not adding vectors. Vectors should be added head to tail. So I slide this guy over to there, and if I'm just going to sketch this out, I'll do this in purple. Okay, if I sketch this over here, repeat it approximately. This is, we're just going to guess this, and then I come back and I slide this back down. This better work. Obviously, that's not 35 degrees. Woo! Okay, that's not good. Then I got to end up with no vector at all, because this. Oh, okay, fine. This comes up like that. And that's about parallel, and then you add up this. Voila. RW, MG, okay, moved over. FP moved over. BW moved down, and sure enough, no resultant. All right, that's cool. Okay, I guess we're done. Feel all right.